continuar con el simposio. Esta tarde vamos a tener 3 charlas sobre el tema que estamos hablando, ¿no? Entonces, me da mucho gusto que las primeras 2 charlas de la tarde las van a dar 2 jóvenes investigadoras que están a punto de obtener su grado de doctoras y van a presentarnos su trabajo de doctorado. Ya, como muchos de los alumnos del curso, ya les tocará a ustedes presentar su trabajo de doctorado en algún foro. Entonces, a mí me da mucho gusto que en esta ocasión las circunstancias hayan favorecido que sea así y que ellas vengan y presenten su trabajo. Me gusta porque para ellas es una oportunidad, para nosotros es una oportunidad de oírlas y para ustedes también, porque ustedes se den cuenta que al final de una serie de semestres de trabajo y de experimentos y de todo, ustedes van a tener un producto terminado, cabal, completo, en donde ustedes hicieron una o varias preguntas y las contestaron y pueden presentarlo y discutir su trabajo. La intención es esa, que el día de hoy ellas dos tienen un foro magnífico para presentar y discutir su trabajo. Entonces me da muchísimo gusto. Voy a presentar la tercera persona que va a dar la charla, la va a presentar el doctor Velázquez más tarde, pero es ni más ni menos que la doctora Constance Jeffrey, que es la persona que acuñó el término Moonlight. Y ella ya les contará por qué lo acuñó y qué quiere decir. In the different Englishes that are speaking along the world, it's not the same, the English that's speaking the USA, that in which English is this not understood what Moonlight means? Vandalism at night in India, because moonlight is what you do when nobody sees you but the moonlight. Todos hemos hecho algo a la luz de la luna, científico o de cualquier índole, desde preparar alcohol y todo lo demás, ¿no? Así se hacía durante la ley seca, el alcohol se producía. Entonces no nos es ajeno, pero ella tiene una explicación mucho más interesante de la que yo puedo dar haciendo estas alusiones. Pero realmente es un gusto que Connie has accepted to be with us today and to tell us about her project and things and to listen to all the works which have been presented. During the whole day we have been analyzing what a moonlight protein is, how can you predict if some protein has a moonlight property, and various other aspects. So the first person that's going to speak this afternoon is Adriana Espinosa Cantu. Ella, he is from the laboratory of Alexander de Luna, who is here with us, and I will only read what he works in genetic systems biology, and he says he's stating what they do in his laboratory in Langevio, in Irapuato, in the Simposio in Irapuato. We are a multidisciplinary lab that studies gene function and evolution at the systems level. We build and analyze large libraries of these mutants in a systematic effort to understand how genes, the environment, and their interactions influence complex cellular phenotypes such as growth, survivorship, and aging. We use robotic integration to explore how gene expression affects fitness, and how duplicate genes impact functional innovation and biological robustness. So they have a very important research programs based all the time in synthetic biology and in analyzing a lot of mutants. Today, Adriana will talk about her work, which is entitled A Systematic Genetic Screen for Moonlight Enzymes. Many of the moonlight enzymes we know that are moonlight have been found by chance, by accident. Somebody found, oh, it's doing something else. How is this? And so they went ahead and tried to characterize. Some others have been found directly, like the work that was presented this morning by Ana Lilia. She explained to us how did she find and how did she ask whether LIS20 was a moonlight protein, and she found it was, and she found the role it plays. So, but today right now we're going to listen to another research, another focus, another approach to the research of these proteins that is a systematic genetic screen. I'm going to do something to make a question as to several genes and see how I can determine whether there's a protein that can moonlight. So I'm very happy to present Adriana Espinosa Cantu, which is a rehearsal of her examination that will be very soon. So please.
Thank you very much for the invitation and the presentation. And I'm very glad to be here in my alma mater, so thank you for the opportunity. So, Vygotsky, in a very famous book called Gene Sharing and Evolution, asked us to imagine an alien coming to Earth and studying life. And he asked us to imagine this alien and seeing the first chair, and then he might think, or it might think like, oh, what a perfect device to hold doors, because this particular chair was holding some doors. But then, a few days afterwards, it arrives to an auditorium just like this and sees a lot of people sitting on chairs, and chairs are empty but arranged, and says, oh no, now I'm confused on what are the functions of these chairs, no? And Vygotsky says, well, this is what's happening to us of all these years of genetics. We usually think that genes are non-functional entities with a particular molecular function that we identify first on them. But well, for many years now, we have described different mechanisms of gene multifunctionality. And moonlighting is one of the last that has been described. As Alicia told us and Jeffrey's going to tell us next, moonlighting refers to people that have two jobs, especially one at day and the other one at night. So these moonlighting proteins have two independent molecular activities. And very importantly, they are not the result of gene fusion or alternative splicing. So that makes it more difficult to identify by sequencing, as we were perfectly explained before in the morning. And well, just to have an example, the aconitase, well, has a very well characterized molecular activity, an enzymatic activity, of the conversion of citrate to isocitrate. But in yeast, it's known that it has a moonlighting activity where it binds to DNA, mitochondrial DNA, and functions as a histone-like protein. Also, or in another example, in humans and in some bacteria, this same enzyme, the aconitase, functions as a regulation of translation. So, as it's evident in this case, moonlighting proteins are not easily identified by homology between species, because they can be volatile sometimes. So the activities in moonlighting proteins are said to be independent because you can have a mutation that eliminates, for example, the enzymatic activity while retaining the moonlighting, and vice versa. And nowadays we have around 300 examples of different proteins in different moonlighting proteins in different organisms that are doing a lot of different activities. And they seem to be an excellent model to study the evolution of function, because, well, you're not studying only the evolution of a function, a single function in a polypeptide, but now you're studying the evolution of two independent molecular activities in a single polypeptide. So in the lab, as Alicia told us in the introduction, we're interested in studying how molecular activities may evolve in a molecular point of view, but also in a genetic systems point of view, and also throughout speciation. So we're interested, for example, in understanding how can two functions be origined and conserved in a single polypeptide, and if there are some functional trade-offs, how can they circumvent these problems, and how moonlighting proteins evolve in a genetic systems, so where you have tuning and different expression patterns and different kind of interactions, if they are visible, genetic, and also in understanding what are the characteristics of these molecules and genetic systems that make moonlighting proteins to be prone to be volatile or conserved. But, well, to answer these questions, we would like to have a lot of examples of moonlighting proteins, and we still need to characterize more of them because we're sure there are more to know. And so the problem is how to identify these proteins. And what I have been doing in my PhD project is to develop a strategy to directly test if a gene can be moonlighting or not. So our strategy is based on simple genetic, in classical genetics, where you compare the growth phenotype of different strains in different growth conditions. For example, with this oxidative stress or DNA damage, and the strains we compare are three: a wild-type strain, that has a wild-type protein gene and therefore protein, a strain with a knockout that has no gene and therefore no protein whatsoever, and a catalytic mutant that is the result of a point mutation that changes a catalytic amino acid and therefore depletes the catalytic activity. And in this model example, the wild type grows perfectly well in all the conditions, while the knockout has a severe phenotype. And now the question is, how is the catalytic mutant growing? And there are two scenarios. In one, the phenotypic profile of the catalytic mutant is just the same as the knockout, and therefore the loss of catalysis is explaining the whole phenotypes of the knockout, and therefore we are seeing a monofunctional, at least until proven guilty, protein. But in the other scenario, we are seeing that the profile is dissected, and some phenotypes of the knockout are explained by the loss of catalysis, while the others are not. So this might be implying that there are other functions rather than catalysis that are driving the phenotypes in the knockout. Okay, so to test our strategy, we chose enzymes from the least amino acid metabolism. And why these enzymes in particular? Well, because it was easily to find enzymes with three characteristics that, well, many of them are characterized as monofunctional. So right now we think that they only have one molecular activities. The other characteristic is that they are very well characterized biochemically, structurally, and so it was easy for us to design a point mutation that eliminates the catalysis. And the third characteristic that we looked for was that they are isotropic for an amino acid. So that made us really easy to prove that the mutations in the knockout and the catalytic mutants were loss of catalysis, were the loss of function that we were looking for. So for each of these 19 genes that we chose, we constructed the strains we needed, and we constructed them by generating knockouts and then complementing them with centromeric low copy plasmids with either the wild type sequence, no sequence, and the sequence of the gene with a point mutation that we designed in order to eliminate catalysis. And for some genes that we tested, we have only 1 point mutants. For others, we tested 2 point mutants that give the isotropy that we searched for. And for genes that have paralogs, what we looked for was to characterize them under the single gene deletion background and with the deletion of also the paralog. And this is to try to see when paralogs have the same function, well, to eliminate the redundancy and be able to see phenotypes. So, long story short, for all the strains we characterized, the biological replicates, the conditions we tested, we followed around 4,000 growth curves, and this was, well, I was able to do this because we have a great robotic system in the lab. And all the results of these thousands of growth curves can be resumed in this graphic, where we are seeing the growth rate of the knockout versus the growth rate of the catalytic mutant, all relative to the wild type. So a result near 1 implies that all the strains are growing alike. Like in this particular case of threonine deaminase, where we see that the wild type in black, the catalytic mutant in orange, and the knockout in green don't have a significant difference in growth. And alike these, 54% of our data show these monophenotypic results. On the other hand, we identified some cases where both the catalytic and the knockout have a severe phenotype compared to the wild type. So these are catalytic dependent phenotypes, and around 22% of our examples were like this. it was also nice to see that only 3% of the cases were those where the knockout grew even better than the catalytic mutant. And this is an example. In another medium, these strains, the catalytic mutant is growing worse than the knockout on the wild type. And these cases might show the ones where there are structural defects, for example, in the catalytic mutant, or where there is an alleviating effect of eliminating the production of the whole protein in the knockout. What we were really interested in looking for were these cases where the knockout grows worse than both the wild type and the catalytic mutant. And to our surprise, it was around the same percentage of cases giving us catalytic independent phenotypes than those that were catalytic dependent. So the next thing we want to know is how these phenotypes are distributed among our query genes. So here I present you a heat map where only the significant catalytic independent phenotypes are colored. And each one of these blocks represents a gene with different constructions, for example. So these big ones are with parallels. And what it can be immediately seen is that the moonlighting behaviors are grouped in 4 genes in particular. And these genes are the threonine deaminase, the acetylated synthase, the branching transaminase, and alanine transaminase. So at this point, we were really happy of identifying these genes, and we wanted to follow up some of these to try to characterize what is the molecular nature of this moonlighting behavior we are observing in the genes. And what I'm going to talk to you about is on our work on characterizing threonine deaminase, and at the end of my talk, I will briefly return to talk to you about these 2 proteins briefly. So, to try to understand what is the other molecular activity that we are seeing in threonine deaminase, we used a very useful tool that is called genetic interactions, because genetic interactions have been used to identify functional relationships between genes based on this approach of guilty by association. So if you have genetic interactions with different groups, then you can try and predict that you can have parallel or similar molecular functions. By now, I think that you can imagine that what we were trying to do, or what we tried to do, was to divide interactions between those dependent on catalysis and independent of catalysis. So, in brief, genetic interaction is described by the phenotypes of single and double knockouts. So, the phenotypes are indicating different fitness properties. In this case, we are seeing, for example, the colony size. So, imagine that you have a deletion in a gene and another gene, and the question is, how is a double mutant growing? And there are different scenarios. In one, it's worse than that you would expect by chance, and this is called aggravating or negative genetic interaction. And it is usually found in genes that work in parallel. So eliminating one might have as a phenotype, a decremental phenotype, for example. And then eliminating the other is worse because now you're not having the product of the 2 activities. Then, if it's the same as expected by just adding the effects, then there's no interaction, and there's another possibility that Olivia told us before, that it's alleviating or positive genetic interaction in which the double mutant grows even better than expected by the single deletions. And in this case, then you could expect, for example, that the proteins are working the same pathway, so eliminating one has an effect, but then eliminating the other one doesn't really add up, no? It was the same. So to try the genetic interactions in our model, threonine deaminase, and to divide them into catalytic dependent and catalytic independent phenotypes, we did 3 libraries. With the knockout, the catalytic mutant and the wild type through indeterminate, and do the double deletions with a library of 3,800 knockouts. That it's almost all the non-essential genes in GIST. So we grew the double mutants in hydrogen peroxide, where we had seen the catalytic independent phenotypes, took photos and extract colony sizes, and then we got the S-score that it's giving you the genetic interaction measure. So these are all the data of the S-scores, and we see that a lot of them have no interaction, and that's what we would expect. And then a lot that have negative interactions and some positive interactions. And of course then we divide them between catalytic dependent and catalytic independent phenotypes by C-scores. And what we found was that these genes were enriched. So we asked for the non-catalytic interaction enrichments, catalytic interaction enrichments. And what we see here were the GO terms that were enriched by catalytic dependent gene interactions. And they were from protein transfers, for example, or victim protein processes. And what we see is that although most of them were catalytic interactions, there's a small fraction that was also from non-catalytic genetic interactions. So these could imply that maybe there are some crosstalks, and therefore we cannot divide them completely. So there are some, what we are proposing is that there might be crosstalks between the enzymatic activity, known enzymatic activity of threonine and the moonlighting activity of the same protein. On the other hand, there were non-catalytic interactions, especially in protein assembly GO terms, and in particular this respiratory chain biogenesis. So we wanted to verify these results, and what we did was to try to do the novel double mutants and do this spot dilution analysis. So what I'm showing here is the growth of wild-type knockout and the catalytic mutant in hydrogen peroxide. And well, we see the moonlighting phenotype. And the question was, how would they grow with the other gene deletions? And first we tried with a gene that was catalytic dependent. And we confirmed here that the double deletion with the catalytic mutant grows even worse than the knockout double mutant. So this is not a sort of big surprise to us, because threonine deaminase is working in the production of amino acids, and this gene in particular activates it's a activate permease that led the amino acids to enter the cell. On the other hand, we tested genes that were non-catalytic interactions, and we confirmed, for example, in this gene that is a chaperone needed for the mitochondrial respiratory chain assembly, that the knockout has a defect in growth from around 2% compared to the one with a single deletion, while the catalytic mutant grows as the same. So we confirmed this with another 3 genes involved in this mitochondrial respiratory chain assembly. Another way of testing this is by chemically inhibiting the mitochondrial respiratory chain. And because many of these genes are involved specifically in the assembly of cytochrome C, we used ¿cómo se dice en inglés? Cianuro de sodio, sodium cyanide. And what I'm presenting you here is that epistasis. This is the difference of growth, from the expected growth of the double mutant in hydrogen peroxide aumento en peróxido de hidrógeno, and in un gradiente, in a gradient. So in green we are seeing the knockout, and in the catalytic mutant we are seeing here in orange. And what we see that the epistasis is stronger in the knockout. So we are seeing that there seems to be another function that it's not catalysis with the threonine deaminase, that is parallel to some of the functions of the cytochrome C, because the cytochrome C is not only needed for respiration, but also for another type of activities, as apoptosis or signaling by auxiliary directive species. And well, at this point, we still do not know what is the exact molecular activity that we are seeing in the protein, but we have an idea of what can it be. So for the last couple of slides, I want to return to our evolutionary questions. And so their duplicated genes have been used for a long time also to study the evolution of molecular activity. And they are known to be like mechanisms where innovation is possible. So in our lab, there's a historical tradition to work with duplicate genes, because my advisor worked with Alicia, and then he started to work with the systems, the genetic systems evolution of duplicated genes. So of course we turn and look on what is happening with the duplication of moonlighting proteins. And what is usually discussed in literature is that when a moonlighting protein is duplicated, then the functions are divided in the paralogs, and the outcome is to have monofunctional proteins. So in a canonical example, we know that these two proteins were moonlighting in the ancestor, and when duplicated, the proteins in Saccharomyces cerevisiae got each one one activity of the moonlighting ancestor. But when we looked to the databases that are available now of moonlighting proteins, we see also a lot of examples like this, where the paralogs are moonlighting both. So we don't know exactly if the ancestor was moonlighting, but well, it seems parsimonious to think so. And these are kind of adapted in each paralog. So, although enolases have both the moonlighting activity, they have been adapted, or they have been optimized to do even the catalytic as the moonlighting activities. And a lot of the other examples in the moonlighting databases are like this, where only one paralog has been described as moonlighting activity, while the other one has only one of the activities, like the one Anna Lilian told us in the morning. But actually, when reading the literature about these examples, what we found is that a lot of them had evidence that they more probably are these cases. For example, the exokinases, in which only this one is moonlighting. If you delete this one, this is overexpressed, and it can rescue the moonlighting activity of the other exokinase. And there are also a lot of examples, like these ribosomal proteins, in which it can be suggested that it's more like both proteins are conserving the moonlighting activities after gene duplication, because, for example, this one in particular are 100% conserving the amino acid sequence. So, although they're actually not very much diverging in expression patterns or localization sites in the cell, so we suggest that maybe we have not been characterizing them so thoroughly, and that this case might be more prevalent than we previously thought, and therefore duplication might be not only important for the solution of trade-offs in a moonlighting protein, but also for the maintenance and further adaptation of moonlighting proteins. In our example, in our genetic screen, what we found with these proteins are that, well, for example, this branching amino acid seemed to be moonlighting in many of the media that we tested. And the question was, well, what is the interaction with the paralog? So what we're seeing here is that although in some of these media the moonlighting phenotype is conserved, in a lot of them it disappears. So this is implying that the moonlighting phenotype or behavior that we are seeing in these experiments are dependent on the presence of the parallel. This could mean a lot of different scenarios, but maybe the parallel is regulating the moonlighting activity of the branch-change amino acid. On the other hand, we see that this alanine transaminase has also a lot of moonlighting phenotypes, and when we compare it with the double mutation background, we see that they are conserved along many of these media. So this seems that there's no redundancy at all in the parallels. So it's the same of having one, only this one, or having both. The moonlighting phenotypes are conserved in alanine transaminase. So saying this, until now, it seems that we are, with the dissection of phenotypic profiles, we are exposing these moonlighting behaviors, and we have identified 4 genes that have consistent moonlighting behaviors. The dissection of genetic interactions of threonine deaminase shows that it may have a mitochondrial homeostasis role that is independent of catalysis, and if we continue doing these kinds of analysis, we can shed light into different scenarios on how our protein moonlighting, how our moonlighting proteins evolving, and how is duplication, gene duplication, working in these kind of molecules. And with that said, I want to thank the people of my lab and you for your attention, and I will take any question.
One parallel is in one and the other one is in another. Does not that could affect this kind of analysis?
Yeah, sure I think, but we are seeing everything here is under the natural promoters, no?
Yes.
So maybe some kind of expression or under some kind of, how do you say, stresses, they are co-expressed in some cellular localizations. And as Ana told us, there may be forming heterodimers, they might be interacting somehow. Mm-hmm. Maybe the interaction is not physical or it's not direct, but it's on direct, like by gene regulation or by metabolic cascades.
It has been recently found that that one interacts with aconitase in the mitochondria. I wanted to make this experiment, but I was not able to see whether this capacity could be substituted by Cantu, because it was considered as a moonlighting, the fact that it could interact with aconitase. But it can do that, BAT1, because it's in the mitochondria. While BAT2, which is not, cannot do that, but maybe you... I mean, it's just an example of something related with BAT1 and BAT2 that is interesting, because it depends on the localization of the protein. Just... ¿Qué más? Alex, a ver, perdón, Gabriel.
So I have 2 questions. The first one, we were talking about this issue of multi-domain proteins, and so it's not clear to me if in your selection of enzymes you were selecting proteins that will have not multiple domains that came from different genes.
So sure, we didn't reduce our query proteins to monodomain proteins, but any of our query genes were product of gene fusion, or if they do, they do not have any known activity independently. So Right now, what we have are enzymes. Some of them need the two domains to have the catalytic function, so they do not have the catalysis independently. And yeah, to any one of these, there's another activity, or there are no activities known by any of the domains independently. So I was talking with Jeffrey before, and it seems that we still have a lot of things to learn about moonlighting proteins. Because, okay, from one side, we know that there are some gene fusions. And from the other side, we know that there are multifunctional monodomains. But then we have all these gradients, right? We have multi-domain proteins that might be moonlighting, as we have known by literature. And maybe, at some time, we will learn that these ones, characterized as moonlighting, have evolved somehow by gene fusions that we see, or by the activities have evolved independently in some species by gene fusion, but in another ones not. So there's a lot of gradient between gene fusion and moonlighting that we still have to explore.
But in your case, the enzymes that you picked are what kind of proteins?
They are mostly multifunctional, multi-domain, but monofunctional.
Okay, thanks. The other question is, you mentioned that all these enzymes are auxotrophic, the division. The null mutant is auxotrophic.
Yeah.
That's correct, right?
Right.
So I'm curious to understand why in your screening you didn't consider to look for moonlighting in the auxotrophy of these mutants. To ask if the catalytically inactive mutant was not the reason why the null mutant was auxotrophic.
I'm not following you, sorry.
So, why, let's say, for example, for isoleucine, ILE3, you know that if you don't put isoleucine, the null mutant won't grow, right?
Sure.
So then, why don't you try to test the catalytically inactive ILE3 to see if the enzymatic activity is the one that is causing the auxotrophic phenotype? I don't understand why, instead of testing so many different media, you didn't try that one in particular, which to me was the obvious because it was part of your selection, right?
So, if I'm understanding you correctly, you're asking me why didn't I took the minimal medium and tested the growth of the catalytic mutant and the wild type. Is that correct? Well, the catalytic mutant can grow in minimal medium also. By definition, they deplete the catalysis. But
By definition or by your observation?
no, by definition of our system.
So the minimal medium doesn't have the amino acid.
No. So they cannot grow neither the knockout nor the catalytic mutant.
Oh.
Yeah. So that's how we selected our catalytic mutants.
So the auxotrophy in all these cases was explained by the lack of enzymatic activity.
Exactly.
In all your cases.
Exactly. But also, if I'm understanding it correctly, we could test the. Okay, no, maybe it's longer than I would expect, and we can talk later. Okay.